right, now we're looking at linear transformations. And so what we have generally with a linear transformation is some sort of function that holds true for these two properties. So we need to test these two properties to know if we have a linear transformation. I'm not going to rewrite these. I'm just going to write it down here. And we should notice that our function t can map between two dimensions. So if we look at this first example, we notice that our function f, and of course we can call functions any letter that we want, so looking at f, we're mapping from R2 to R. So the first thing we need to test is that f of some vector u plus v is going to equal f of u plus f of v. So that's what we're looking for here. So f of u plus v, that's going to be f of some x1, x2, y1, y2. If we plug this in, we're going to have x1 plus x2 times y1 plus y2. This is going to work out to be x1, y1, x1, y2, plus x2, y1, plus x2, y2. But if I took f of u1, f of u plus f of v, that would give me x1, y1 plus x2, y2. These are not equal to each other. So I can stop right there, f of v, and say this is not a linear transformation. All right, so let's look at our second function. I'm going to make this a bit smaller so we have some more space to write. All right, in our second function, let's test out f of u plus v. So that's going to give us, let's look at this. This is going to be 2x1 plus x2, y1 plus y2, minus x1 plus x2. I could expand this to be 2x1 plus 2x2. This one I could separate out to be y1 minus y2 plus, y1 minus x1 plus y2 minus x2. And notice if I separate my vector addition, that's the same as f of u plus f of v. So that one holds. If I test f of k, u, where k is a constant, I would get 2kx1, and down below I would get k times y1 minus x1. I can factor out the k, 2x1, y1 minus x1, which is the same as k times f of u. Therefore, this is a linear transformation.